comparison test only works for series, not sequences. The theorem for the limit comparison test is: suppose that a of n is greater than 0, b of n is greater than 0, and the limit as n approaches to infinity of a of n over b of n equals to L, where L is some positive and finite number. Then the two series, a of n and b of n, either both diverge or both converge. So basically, the steps are to know your givens. Number 2, decide what to compare a of n to. Number 3, take the limit of n approaches to infinity of a of n over b of n. Number 4, find if L is positive and finite. Number 5, it is to test for b of n for convergence or divergence. And number 6 is to find your answer. In our first example, we have the series of 3 to the n all over 4 to the n minus 1. We can compare this to 3 to the n over 4 to the n. We can say that a of n equals to 3 to the n all over 4 to the n minus 1, and b of n equals to 3 to n all over 4 to the n. By the limit comparison test, we can find the limit of a of n divided by b of n. By doing this will lead us to the answer of 1. One is positive and finite, so the series could either converge or diverge. The series of 3 to the n all over 4 to the n converges by the geometric series test. Therefore, the series of 3 to the n over 4 to the n minus 1 converges by the limit comparison test. For our second example, the problem is the series of 2 over the square root of n squared minus 1, which we can compare to the series of 1 over n. A of n equals to 2 over the square root of n squared minus 1, and b of n equals to 1 over n. Now, we can take the limit as n approaches to infinity of a of n over b of n. get 2, which is a positive and finite number. Because of this, we can now use the limit comparison test. 1 over n is a harmonic divergence series. The series diverges. Therefore, by the limit comparison test, we can say that the series of 2 over the square roots of n squared minus 1 diverges.
For this example, we compare n squared to n. Then we set up the limit comparison test and plug in b sub n and a sub n, with a sub n equal to n squared and b sub n equal to n. After we simplify n squared over n to n, then we must take the limit by plugging in infinity. Since the limit approaches infinity, therefore the limit comparison test does not apply because infinity is not a positive nor finite number. Therefore we must use another test to find whether the series converges or diverges. So for our final example, we have the trig series of sine of 1 over n. So we notice that we want to use limit comparison test, and for that we must also have a b sub n, which in this case we will use 1 over n. First we must take the limit of a sub n over b sub n, which would be sine 1 over n over 1 over n. This simplifies into limit as n approaches infinity of n sine 1 over n, using copy.flip. This however ends up equaling 0 over 0, so we can use L'Hopital's rule. Now we can take the derivative of the top, which is negative 1 over n squared, times cosine 1 over n, and derivative of the bottom, which is negative 1 over n squared. This simplifies to cosine 1 over n. The limit as n approaches infinity of cosine 1 over n equals 1. Therefore, limit comparison test applies. Since we compared the series sine 1 over n to the series 1 over n, and the series 1 over n diverges because the series 1 over n is a harmonic diverging series. Or we can find this by using p-series, because since p equals 1, which is less than or equal to 1, therefore by p-series, the series 1 over n diverges, and therefore by limit comparison test, the series sine of 1 over n also diverges.
Thanks for watching. We are Michael, Mikey, Mikhail, and Jim.